vector makes with the xy plane?
False.
Yeah. And why is it false?
Because it's measured from the positive x-axis
Right.
plane.
Yeah. So if instead it was measured from the xy plane, what you'd have to do is you'd have to take the projection of this vector onto the xy plane, and let's say that, or sort of the shadow that it makes on the xy plane. So let's suppose that this is the shadow it makes on the xy plane. What it's arguing is that alpha is instead this angle. But everyone, you guys see that's not what alpha is, it's actually this angle here. This would be the angle that the vector makes with the xy plane, whereas alpha is the angle that it makes with the positive x-axis. So there's a slight difference there. So yeah, the answer would be false. Are there any questions about that?
Are we allowed to take pictures of these?
Yeah, go ahead.
Would you say if we're pretty comfortable with all the stuff we go over today, we should be fine?
You should do pretty well, yeah. So, next question.
I just heard that it's the word
Yeah.
I was like,
Did you find the where alpha is by just plugging in cosine? Or I didn't know alpha was there.
That's the definition of directional cosine, is that the alpha is the angle that it makes with the x-axis. Just like beta's angle makes with the y and gamma's angle makes with the z. It's just the definition of directional cosine.
And I think also, you can correct me if it's wrong. So this is he's telling you that this is true. He's telling you the directional cosine of the unit vector, is this true? So if this is alpha in the x coordinate part, then this is x coordinate goes with the yz plane, right? So not the xy. It would be with the yz plane. It's always the plane that's not the other two. Okay. So next question. So A plus B cross with C. Does this equal minus C cross A plus C cross B? So, first of all, this is telling us we need to do some rules relating to how cross products can distribute out, right? Distributive property of cosines. Let me make sure that this is equal. You don't understand this. The negative sign is part of it, right? Okay. So now, first, unrelated to this question, but I kind of want to ask, so what does the cross product tell you? Yeah.
It creates a normal vector going up from the crossing of the two angles, and it's 90 degrees on the outside, and its magnitude is equivalent to the area of a parallelogram that's made by the joining of the two vectors.
So the idea is that you're going to give it two vectors, and you write about the area, and it's going to give you a resultant vector that's 90 degrees, so orthogonal to both of those input vectors, right? And that's, so cross product, you give it vectors, right? And what is its result after you take the cross product? Is it a scalar or a vector? Vector, so, right? That differs from the dot product, where the dot product more tells you what? What is it?
It's like how much in the same direction they go.
Right. So how much of one vector is in the direction of the other vector, and so that result is a scalar, right? So just for the general exam, make sure that you know that basic concept. Anyways, it's not related to this problem. So we know, hopefully, that the cross product actually is distributed in the way that this could be simplified down to say that I have A cross C plus B cross C, right? So this is true. But then, does that really look like the right-hand side? Not yet, right? But, so one thing, if I take A dot B and I have B dot A, does A dot B equal B dot A? Yeah. Okay, and that's because it's just a constant, right? It's a scalar. There's no difference. It's just how much of that one vector is in the direction of the other, or how much of the other direction is in the direction of the other vector. But cross product is different. If I cross A cross B, and then if I do B cross A, I will get the exact negative answer of what I had from the original one. So we could rewrite this to say negative C cross A. So this is the same. And then another minus for C cross B. And then this you could equate to B, the same thing. So this is what, true or false?
It's true, false, so we wouldn't even have to show that, right?
No.
Okay.
But you could maybe visualize it, but I mean, there's scratch work. Feel free to write it out because sometimes they can be tricky.
Right. Do they get like more
shit.
complex than that? Or?
Oh, Rufus, my bad.
I'm already recording this whole thing.
Oh, cool.
Oh, awesome.
Okay, you took a picture of it then?
Yeah.
Okay, alright, okay.
Because it's not exactly streaming on Discord, I just recording it.
Are you gonna put the video on Discord?
Yes.
Yeah. Thank you.
Okay, so this question is projection of this vector curve onto the xy plane, a circle with radius a. So, by looking at the x and y components, you see that just the two of those, that traces out a circle, and we see that the radius of that circle is a, and t makes it go up with time, so it's like a helix shape. But if we were to project this onto the xy plane, that would mean that the z component is equal to 0. So we would actually just get a cosine t, a sine t 0, which is in fact a circle of radius a, so it would be true. Are there any questions about that? Pretty straightforward. Okay.
Right, the idea of projection means that I'm looking at, remember that quiz that we had this week, right? Where we projected that scary graph onto different axes so we could look and we tracked it along so we could see the behavior of the graph. But this is asking us just look top down, right? Remember, at least in my discussion, we looked at GeoGebra and we looked at it in certain ways and would just kind of look like either a parabola, a circle, or I don't remember exactly all of it, but like, we could look downwards on it. So if you look straight downwards on this, it's going to look like a circle, right? So that helps you in 3D stuff try and figure out what's going on by looking at it in different ways, right? Here it's a pretty nice side image, but if you looked at it one way, the other way, and top down, you could also recreate that 3D. Okay. So, the next question. The next question. So does anyone have any thoughts about this? If two lines are parallel to a plane, then they're parallel to each other.
I think it's true.
Okay.
I don't have any
Okay.
other.
Does anyone oppose?
I think it's false because like if you have a plane, it's orange. You still
It could be
have
like this
two axes.
and this.
Right. So what does it even mean to be parallel to a plane, right? Like this is a plane, right?
Right.
This table, right? This vector is parallel to it. It's on it, right? But so is this one, right? Now, if two lines are parallel to another line, are those two lines parallel to, yeah, there you could say. But to a plane is an interesting wording, right? If two lines are parallel to a plane, then they're parallel to each other. It doesn't have to be, right? And it's not even dealing with skew or anything. It's literally just the definition of plane doesn't really lead to any strong correlation with parallel. So, see, this is the kind of thing to watch out for on the exam. That you read it, okay, yeah, it sounds good. And then it's like if you were to actually go down and read it, may not be true. Or maybe true. All right. So for this one, actually, this is. I think we can also write some equations that look at because this will get an equation. We should have one like equation board.
Sure, yeah. You want me to write the equation or? Oh, you're writing the equation. Okay. Okay, so for this question, we're given two vectors. We want to find the vector projection of u onto v. So if we have, this is the vector u, and this is the vector v. We want the vector that points in the direction of v with magnitude of the magnitude that you would have as the shadow of you onto v. And for that, we will use the following equation. This is the projection of u onto v. So projection of u onto v, you sort of write it like this way. You start at the start, you go to the end, and then write v at the bottom there, if it's worded in this way. And this will be equal to the dot product of u with v over the magnitude of the vector that is in the subscript there, which is v, and then times the vector v, like that. So are there any questions so far about that? Yeah. Okay, so we'll just plug stuff in here. So u is going to be, this vector here, 2, 5, minus 1. And we dot it with v, which is 3 minus 4, 6. And we divide this by the magnitude of v, which is the square root of the sum of squares of the components of v. And then multiplied by that's right there. You don't have to square this, you have to multiply this by unit factor v. So that's equivalent to dividing v by its length again. So just square it there. Okay. Alright, so we'll just go ahead and repeat what this result would be. So we'll have 2 times 3 plus 5 times minus 4. And then plus minus 1 times 6. So the square root and the square get canceled. So we'll have 3 squared, which is 9, plus 4 squared, which is 16, plus 6 squared, which is 36. Then we can just simplify this. So this will be 6 plus minus 20, and then minus 6 over, so 9 plus 16 will be 25, plus 56, you get 51. So then these 6's will cancel. You'll get minus 20 over 51.
Isn't it 61?
Or is it
61.
But it's 25 plus 36.
I've done this before. I remember making this mistake in a previous time that I went over this exam, I'm pretty sure. Oh yeah, so then we get this, and, oh, then we have to multiply by v. You know about that? So then we'll just have v, which is 3 minus 4, 6. And you get that.
Are you okay with that as the final answer?
Yes.
Or?
I mean, here you'll be given, options, A, B, C, D. So, if you can simplify down to the answer that he gave, then you should do that.
Gotcha.
So just because this doesn't look exactly like what you have, doesn't mean that it's some other answer. Maybe you can simplify it, it could be.
Okay. Thanks.
Huh? So, okay, also one thing with this, many people make this mistake sometimes, right? So, first of all, notice here that this is the projections, either the component or projections, but it's of B onto A is the way that this is written, right? If you're doing A onto B, then A isn't in the denominator, right? It flips. So if he asks me, he defines A and B, and he asks, please find the projection of A onto B, this isn't going to be the equation. It's going to swap. And so many people forget, they're just like, oh, A goes in the denominator. It's like, well, it depends on what he's asking. If it's A onto B, then it's one way, or if it's B onto A, it's the other. So just make sure you know this equation, and you know what is onto what for the way that you've memorized it. And then you can adjust it. All right. So, now, we're going to think of something. You think we should do or skip? Why not? Okay, so imagine you have a cube, okay? You have a 2 by 2 cube. And so the center is the origin. And inside of this, there is going to be a unit sphere.
And it's centered at the origin.
Centered at the origin.
What is a unit sphere again?
So it's there with radius 1.
What?
Sphere with radius 1.
Radius.
Okay. So expert drawing that we have. However, because it's only a unit circle, the edges, well actually, so this is not correct, right? Here, the radius of the, imagine you cut this cube in half, right? The length from one of the sides to the edge is what?
1.
1, right? Now what's also the radius of that sphere?
1.
1. So they will touch just at this edge, and all the edges, right? Just at the very centers. You imagine there's a cube and then a sphere inside that the same radius as the radius of the box itself. It will only touch at the very edges, right? And the corners, it curves in, so it doesn't touch there. Okay? But he's asking you here, calculate the shortest distance from the very corner of oh yeah, okay. So find the distance from one edge to the sphere.
And the distance from a corner of the cube to the sphere.
And so let's say that this is a corner of the cube. Let's call it point A. And you want to find the distance to the closest distance, to the edge of that sphere. Right? because we know that this is curling in, right? So there's some distance between the edge and that circle. How would you begin to try and think, how could I do that? How could I find distance?
Make a position vector for the corner of the cube, so you can have that, and then you know the radius of the sphere is 1, so that you can
You're very close.
try and
Yes.
find the position vector for
Yes.
that, and then find the difference between
Yeah,
the two.
displacement vector. Yep.
Awesome.
Yep. And then just take the magnitude of it.
Oh, it's literally just that.
Yeah.
Oh, wow.
Or really, just take the magnitude of the position vector for the corner and then just subtract 1 from it, because you know the magnitude of the
It's
vector
gonna
of
be
the
1.
sphere is 1.
Yep.
Yeah, basically.
So we can write it down.
So if I get a vector pointing downwards here, right?
Let's have this be x, y.
Okay. From the very center, it's going to go positively in y.
Basically x, y, and z.
It's going to go 1 in x, 1 in y, and negative 1 in z.
Try to drop that. Yeah, so it'll go like 1 in x, negative 1 in z, and then, oh, actually that would be.
And then positive 1 in y. That. Similar to this, but you go out 1 in x, down 1 in z, and then plus 1 in y. You know, hit point A. And then you think, okay, well, what's the vector? What's the magnitude of the vector that's going from here to the very edge? 1. 1, right? Because it's a sphere, right? So from the very center to anywhere in it is 1. So the n magnitude would presumably be something like the larger one, which we know is the outer edge of the cube, because that's the farther out part, subtracted by the magnitude of the unit vector that's going from here to the edge of the sphere. Oh yeah, the magnitude. Okay. Bit of thinking, right? But it's possible. So whenever you get a question like that, and it's like, if I didn't otherwise know what to do, you'd be a little stuck, but then try and think, what do I know? What can I do? Spheres. Okay, the radius is constant throughout. That I know. For cubes, I know that I can get the distance from the very center to the edge of it, because I know if I can calculate its movement in a vector, then I can take the magnitude of it very easily, right? So you had to use both of those knowledge to come to this, and there may be a different question in your exam. So try and remember this base concept that you know. Okay, I can't do that. I can't do that. Spheres have this property, et cetera, et cetera.
You wanna just find it?
That won't be doable, you have to check every single one, because it won't be unique.
Oh. Well, we can just find what it is.
It won't be unique, and also there's different forms, so the effective one might be much easier. You have to check every single one. This is a specific problem where you have to check every single answer.
plus 6 over 2 equals y minus 2 over 3 equals z minus 3. And d is 2x minus y minus z equals 4. And then some other answer. I don't know what it is.
Okay, so this is a very interesting question. So we have an equation, we want the equation of a plane that's parallel to this line here. So let's just go ahead and draw a picture of that. So we want a plane such that you can place that line on the plane. And this is sort of weird, because it's sort of strange, like how would you find that? But there's an interesting thing that we know about planes is that all planes have a normal vector, and all lines have a directional vector v in the equation r equals r naught plus tv, where t is the directional vector of the line, right? And we know how to find n, because the equation of a plane is usually just going to be n dot r minus r naught equals 0, where if you were to expand this, you would get a x minus x naught plus b y minus y naught plus c minus c naught equals 0, where n is the same thing as the vector a, b, c. Everyone sees that? So we'll always be able to identify the normal vector of these planes, and we'll always know, and we know the directional vector of this line here. It's just going to be what's in the denominator here. It'll be 2, 3, and then 1. And if this line in fact is parallel to the plane, that means that its directional vector will be orthogonal to the normal vector. So if we were to dot the two of them, we should get 0. Everyone sees that? Because the dot product of cosine of theta, which will be cosine of 90, which will be 0. So what we're going to do is we are going to take the normal vector for each of these planes and dot it with the directional vector v. And we are going to check to see if it's equal to 0. And if it is equal to 0, then that's the correct answer. Everyone sees, I know that's a lot. Are there any questions about that? Everyone sees how this will work? Okay. First of all, not all of these are actually planes. You actually see number C, that's a line, so we know that's not going to be the answer, right? So we can just cross this out because we're looking for the equation of a plane, not the equation of a line. And now let's figure out, so what is V here? So V is going to be equal to 2, 3, 1. And now we'll look at the normal factors for A, B, and D. So for A, you see this is in this form here, where the normal vector is ABC. So we have A is 2, B is 3, and does anyone know what C is equal to here? Yeah, it's just going to be 1, because we see this is the same thing as 1 times that. So we have 1 there. So what we'll do is we will take 2, 3, 1 and dot it with that. So we have here that n is equal to 2, 3, 1. And does everyone see that if I were to dot the two of these, we won't get 0 because they're all positive numbers? So I'm not even going to bother computing the dot product. We know it won't be 0. So from that, we know that this is not the correct answer. Now here, this isn't a nice form because we see we already have n right here. We don't really have to look for it. It's given in the vector form, n dot r minus r equals 0. And you see this is all positive numbers. And if you were to dot that with v, you still wouldn't get 0. So that's also not the answer. So let's turn our attention to the last one here. Here we see A is 2, B is minus 1, and C is also minus 1. So we have n is going to be 2 minus 1 minus 1. So here there's actually potential for the dot product here. We have minus numbers there. So we'll go ahead and dot the two of those. So we have,
Dot n
negative 1 times 2, which is minus 3, plus minus 1 times 1, which is minus 1. We see that we actually do get 0. So that ends up being the correct answer, because that means the normal vector for that plane is orthogonal to the displacement vector, or the directional vector, for the line that we're given there. So you could actually place that line on the plane. So it is in fact parallel to the plane. So therefore, this would be the correct answer. Is there any questions? Does that all make sense? Do you have a question?
Oh no, sorry. I was just looking at the equation of the line. I just mixed it up before. I accidentally wrote the v vector as 1/2, 1/3, but I forgot you have to set it equal to t, and then x is equal
Is
to.
this the same thing as x minus x naught over a equals y minus y naught over b, which equals c minus c naught over c.
I forgot that you have to set it equal to t and then move it
Right,
over.
yeah. Okay, other questions? It makes sense? Yeah, okay, cool.
Actually, I do have a question. You said that C does not, because it's an equation for a line, but isn't a plane also defined by a line, in this case a normal vector? Like you could find the velocity vector of C and do the exact same process.
Sure, but at the end of the day, it's asking for the plane. It's
Oh,
parallel, but that would be a line, so,
Right.
yeah.
And watch out for that kind of stuff. Like, if he asks, what is the plane for something, and you give him the answer that's a line, it probably won't be right. So even though you could argue, okay, if the wording says this, that's something that could be like, okay, it looks right, but it's not in the right form, so maybe it's some other answer. That's like one. Okay, so. Where do you go back? It's the same type of problem. So it's just the same type of okay. Guys are good to go. We can, yeah. Okay. Alright, so. Alright, so we have these options. Is X. Yeah. You can use it. Okay, so let's try and think through. Find which lines are parallel to each other. So first, we can see that we have kind of three different ways of being drawn a line here. Right? Being told these are all lines. This is telling us in parametric equations, x is this, y is this, z is this. same as the second line. The third line is symmetric equations, right? So we've equated t throughout all of them and then just ignoring that that equals t. It's not important. The last one is very similar to these ones, except that r of t equals what? R of t is the movement, is my position of the particle. So it's just a description of my x location, my y location, and my z location. Right? Now, this means though that x would equal what? 3 plus 4t, 1 and y is 1 plus 2t, and z is 5 plus 8t, right? So you could all equate this to be in the same form if you like. But it's important for us to be able to know what are the position vectors, right? What is that t vector for all of these three options? Because that's what will determine whether it's parallel or not. If it's going in the same direction, that's fine. The initial point doesn't really matter. It just needs to have either a scalar multiple or negative, same thing, of that position vector v of what it has. So we can go and we can write out the position vectors for all of them. All right, so for one, the position vector, somewhat easy to see, right? So what is it? I know that it's going to come from this part, right, where the t's are. So what is it?
6, negative 3, 5.
Good. 6, negative 3, 5. All right. For the second one, it's also very easy. It's 2, 1, 4. For the third one, right? And in case on the exam you're like, I don't remember, it's in the denominator, numerator. If you forget, remember, how did we get this that they all equal each other? You were saying it also. That this equals
T equals 2, x was 2.
right? So then all of them equal itself to t. So 2x plus 2 equals t. 4 minus 4y equals to t. And z plus 1 equals to t. Right? So if I rearrange so I get x by itself, I'll find that x equals t, that first, minus 2 plus t all over 2. Right? So my t component here is 1/2. Okay? So see, even though you may have looked at this and said, okay, what's in the denominator? It's a 1, right? But it's not actually what my position vector is because the numerator had a 2 in it, right next to the t. So if you get confused, you can go through and you can equate it, -1 plus 1 over 2t, and find exactly what my position vector is for each component. By remembering that we set it equal to t, and that's how we got everything together. And then resolving for what x, y, and z is. For y, I can say that y is 4 minus t over 4, right? So that's going to equal 1 minus 1/4 t. I believe that's right?
Wouldn't it be over -4?
Well, and minus, right? So
Yeah, negative 1/4.
negative 1/4. And then z will equal, there's just 1. Okay? So my vector for my position vector will be 1/2, -1/4, and 1. Right? Okay? So now, line 4. It's very easy. It's just told you. It's 4 to 8. Alright, so now, this is another question. This is kind of sort of a dumb question. Because none of these explicitly equal each other, does that mean that none of them are parallel? No. It can be any scalar multiple, including negatives, right? Now, this does not work. This does not work. This does not work. 5 is very difficult to deal with, right? In scalar multiples with these even numbers that we have. Okay. 2, 1, 4. Here it's not going to equal out because this, I need to multiply this by 4, right? If I multiply by 4, 1/2 becomes 2, minus 1/4 becomes minus 1, and 1 becomes 4. But the 1 and minus 1 here will be different, so these are not parallel. This one and this one, though, look like as a promising way, right? 2, 1, 4, and 4, 2, 8, I can multiply that by 2, and I get the other one. So therefore, line 2 and line 4 are parallel to each other, right? But don't be afraid to go and to say, okay, it looks at a not nice form, I can still find what my position vectors for all of them, and they compare, right? And don't remember, it's not that it's parallel or not, there's also the option of skew, right? Or they can also intersect at a point. It can be perpendicular.
What is skew again?
So skew is when
it's neither parallel nor, nor intersecting, right? Because on a 2D plane, you're either parallel, for example, if I had this, right? If I draw a line, either another line is parallel to it, or at some point it will have an intersection point, right? But in 3D space, it doesn't have to be true. You could have one line that's like this and one line that's like this, right? This line will continue going on forever, this line will continue going on forever, and they'll never intersect. Right? So in 3D space, we have that option of skew also. Okay. I'll erase this from here. But, it makes sense to everyone? Yeah.
Are you not able to dot these to get whether they're parallel or not? Because I thought if you dotted two things, that means they're, and it equals to one, that means they're. Oh shoot, you'd have to find their unit vectors, and then you'd have to dot
If you
them.
cross the directional vectors and it equals 0, they're parallel. You could do that, but it would take.
No,
So this is just a
dot
lot
them and
faster.
there's zero.
Crossing it at 0.
Cross them, yeah.
If you dot them,
It's just the easier way that takes nobody.
Yeah.
So you could dot it, and then you have to find the magnitude of each one, and then you have to do the inverse sign and make sure, inverse cosine. Dot is cosine.
You just have to dot them and see if that's equal to the product
You
of
could.
their lengths.
So if that's true, then that's fine.
Yeah.
But it's not, you can just also visualize that. It's only, you're not gonna have so many of them. There's only so many multiplications that, is possible. It's not like one is gonna be multiplied the square root of 25. Okay.
Wait, square root of 25.
Which is also known as pi. Yes. Remember this, someone said that in my discussions, they were like, what's the radius of this thing? And someone said the square root of 4.
Eight.
4th root of 16.
Minus 2 over 2 equals y minus 6 over negative 1 equals z plus 1 over 3. And then line 2 is x minus 2 over 1 equals y minus 6 over 2 equals z plus 1 over 3.
Alright, so yeah, so we have to determine these lines are parallel to intersecting, and there might be multiple of those. It doesn't necessarily have to be only one of them, because, lines, okay, so.
Just a quick refresher on parallel, we have the two lines L1 and L2. If they are parallel, that means their directional vectors would have to be multiples of each other. If they are skew, that means they're neither parallel nor intersecting. And if they're intersecting, that means there exists some x, y, z coordinate that I can plug into both of these equations, and they would both be true simultaneously. It would have to be the same x, y, z for both of them.
How can it be both of them? How can it be more than one of them?
I don't think I understand your question.
Didn't you said like that it could be more than one? I don't understand.
No, actually, I guess it actually might only be one of these. On closer inspection, yeah, because skew, it can't be either of the two of these. They can't be intersecting in parallel at the same time. Yeah, so yeah, it can only be one of the three of these. Yeah. Other questions before I jump into this? No. Okay, so let's start with parallel. So we can identify the directional vectors for each of these lines by looking at the numbers in the denominator. So we see for the first one, we see that the directional vector v is just going to be 2, minus 1, and 3. And for the second one, we see it'll be 1, 2, and 3. Okay, now to figure out if this vector is a multiple of the second vector, what I'm going to do is I'm going to take the first vector and multiply it by 2, because that way the x component will be the same as v1. And I'm going to see if the y and z are the same as minus 1 and 3. And you'll see that if you were to go ahead and do that, and you took 2v2, you would get 2, 4, and 6. So the x component matched, but you see the y and z, well, the y component doesn't match, so that already disqualifies it. But furthermore, you also see that the z component doesn't match. So that means that the lines are not parallel. Everyone sees that? Yeah. So we know that it is not going to be parallel, so we can just cross that out. Now, it's skew if it's also not intersecting, so we'll check to see if it's intersecting. So if they're intersecting, that means we need some x, y, z that satisfies both of them at the same time. Does anyone happen to see an x, y, z when it would do that? Yes?
Is it 2, 6, -1?
Yes, it is. Yeah. Everyone see that if you were to plug that into either of these equations, you get 0 equals 0 equals 0, and 0 equals 0 equals 0. So they're both true at the same time. So, yeah, we have 2, 6, and -1 satisfies both equations. So they intersect. Okay, so it'll be intersecting. Yes?
Will we ever have a question where it's intersecting, but it's not as easy as just looking at the numerator?
Probably not. I don't think so. Usually there will be like some trick where if you see, you could just make that both equal to 0, or something sort of sneaky like that. Yeah, it usually won't require that much algebra.
The exam's not trying to get you on like impossible things. It's just
Yeah.
look at it and visually know what's going on.
Other questions? This okay? There you go. Cool. So, next question.
Okay, so now we want to find of a plane that consists of the points P being 0, 1, 1, Q being 1, 0, 1, and R being 1, 1, 0. Alright, so we're going to find the equation of plane. So first off, what is the base equation for plane? Yeah.
The normal vector dotted with position vector minus some point.
Okay, good. So m dot with x, y, z minus x naught, y naught. Okay. And that will equal 0. Don't forget the equal 0 part. This is just saying stuff. Equal 0 makes it an equation, right? Okay, so first off, we need then to know that I need to find a normal vector, and I need to find an initial R0 that gets me this equation of the plane. So for my n vector, I realize that I have 3 points that are on this plane. Okay, so let's say we have this plane. If I have 3 points just randomly surrounded, I need to be able to create 2 different vectors that are going out, and then I can cross them because the definition of the cross product will give me something that's 90 degrees to both of them. And so if I give the cross product 2 vectors that are on that plane, the result will be, by definition, the normal vector of that plane. Okay? But one thing to say that's important is that I should be giving it vectors that both start at the same origin point. Right? So I don't want to give it PQ and then QR. I should give it I could also start at Q, I can start at R, it doesn't make any difference, but I should both start at the same point, right? I don't want to give it two of the same. So, we can do this one for example. PQ cross PR, because both are starting at P. Now, to do PQ, do I do Q minus P or P minus Q?
Q minus B.
Q minus P, good. So this will be the point of Q minus the point of P cross with the point of R minus the point of P. Right? Point of Q is 1, 0, 1. So 1, 0, 1 minus 0, 1, 1. Okay. That will be 1 cross with R being 1, 1, 0 minus 0, 1, 1. Right. So let's take that up over here. So I'm going to have 1, negative 1, 0, crossed with 1, 0, negative 1. Let's see what that will be. So first off, make sure everyone knows how to take a cross product. And I also want to make sure that everyone knows why we're taking a cross product. Taking it is one thing, knowing why is another. So we do it because we're looking for the normal vectors. We want something that we spoke of it. For taking the cross product, I'm going to hold my hand over I, multiply down this branch, top right, the top left, the bottom right. So negative 1 times negative 1 is a positive 1, minusing the multiplication down this branch, which is 0 times 0, and that will all be in my I direction. Now, I put a negative sign outside the J direction, and then do the regular multiplication like I did with the others. So I have 1 times negative 1, which is negative 1, minus 0 times anything is 0. Then I go back to addition for K. I hold my hand over K and I do multiplication down this branch, of what I get 0. 0 minus 1 times negative 1, which is negative 1. Okay? So my cross product ends up coming 1, 1, 1. That's not changing. Okay, so now I can continue on and I can say, all right, so I have 1, 1, 1. And I can dot this with x minus, I can choose any initial point I want. I could choose P, for example. So P is 0, 1, oh, sorry, it's just 0, in the x, y minus 1, and z minus 1. And that should equal to 0, right? Okay, so now 1 times x minus 0 is affectionately known as x. 1 times x y minus 1, first of all, am I going to put a comma here or an addition sign? Addition sign, right? Now I'm taking a dot product, my result is now a scalar, it's not a vector. Right? So plus y minus 1, and then here another plus z minus 1 equals 0. So my total equation should be that x plus y plus z equals 2. Right? You move everything over. It just so happened that the question had it on the right-hand side. If this is a free response, this is acceptable. But if this is like option A, right, you need to know how to move stuff over to the other hand side so you can see it. Yes?
It just says an equation of the plane. Does the first one not count with the vectors?
So this is the, like, if the option A is this,
Oh, okay.
like, you're going to need to know that it's the same thing.
Also, Jeremy, like, you shouldn't leave dot products in your response.
Well, so this is not acceptable.
That's not acceptable.
I would leave it to this.
Okay.
You can't leave calculus in the answer. You should, this is okay. This is probably what you'd see. This means that you don't know how to do a dot product. To him, that's what it means. That you just didn't know how to do it. So don't assume on the first exam that, oh, doing a dot product is so obvious, I'm not going to do it. Do it. Now, you could say algebra is so easy, I'm not going to do it, so that's fine. Algebraic stuff like moving -1 to the other side, okay. If you're very concerned with doing it wrong, then you can leave it in a free response. But don't leave calculus 3 stuff there, because that's what he's testing. Okay, any questions on? Okay.
Okay, so we want to find a vector function, which we usually just will denote as r of t, which will be equal to some vector with an x component x of t, a y component y of t, and a z component z of t. That traces out the intersection of this cylinder given here and the plane y equals z. So we'll have to find parameterizations for x, y, and z, x of t, y of t, z of t, such that if we plug them into both of these equations, it'll satisfy both of them at the same time. So looking at the second equation, y equals z, we see that's actually just the same thing as z equals y. So once we find x and y from this equation here, we see there's no z in this equation, we'll just plug in the value of y for z, and z will just be equal to that value. So we'll find x and y, and then z will then have found as a consequence of finding y. So we see we have a sum of squares of terms here equal to a constant. And this is sort of familiar of the form of x squared plus y squared equals r squared, which we learned about with polar coordinates and all that stuff. Where what we do is, to convert this to polar coordinates, is we would make x equal r cosine theta, and y equal r sine theta. So we're going to do a similar idea here. And actually, I should probably write t here, because we'll be using t. So what we're going to want to do is we're going to want to make what is inside of each of the parentheses here we're going to want to make that r cosine t, and this guy r sine t. So that way when we take the sum of squares of them, we're just left with r squared. So everyone sees that? So this way we'll have r cosine t squared plus r sine t squared equal to radius squared. And we see that the radius is going to be 2, because the radius squared would be 4. So then from this equation, we get that the radius will be 2. So we'll plug in 2 for r here. So because x minus 1 is r cosine t, which is, we just said r equals 2, so that'll be 2 cosine t. You see we can then solve this equation for x. Everyone sees that? So then we have x would just be 1 plus 2 cosine t. And we'll do a very similar thing to figure out what y is. So does anyone see what y would have to be using the process we just did there?
2 sine t equals 2.
Yeah. So we'll do the same thing. We'll have y minus
minus 2 equals r sine t, which we said r was 2, so we'll have 2 sine t. So then solving this equation for y, we get y equals 2 plus 2 sine t. So what's z?
2 sine t plus 2.
Yeah, so then since z equals y, z will then just be what y is, which is 2 plus 2 sine t. Okay, so we don't have our answer yet because we have to then write r of t in this form. So then we'll just write r of t as the vector containing x, y, and z there. So we'll have x, which is 1 plus 2 cosine t. Then y, which was 2 plus 2 sine t. And then since z is equal to y, z will also be 2 plus 2 sine t. And so we get this. And that represents the intersection of this cylinder and the plane deck. And furthermore, the question, I didn't write it, but the question also asks you to draw each of these in a three-dimensional coordinate region. We'll go ahead and draw that as well. But before I draw that, are there any questions about what I had done there? Everyone sees how we did that? So we take this equation, and we see we have a sum of squares of variables equal to a constant. It sort of reminds us of that x squared plus y squared equals r squared, that form that we learned for a circle. Or in this case, it's R3, so that circle has no set z height, so it ends up being a cylinder of R3. And we recognize that when we convert that into polar coordinates, we like to make the x-looking term r cosine, and the y-looking term r sine. So we set what's inside of each of those parentheses, r cosine and r sine. And we know the polar coordinates has equal to the radius squared. So we have r squared would be 4. So then from that, we know r is just going to be 2. And we just solve each of those equations for x and y, and we get x is equal to 1 plus 2 cosine, y is 2 plus 2 sine, and then z we get as a consequence of finding y, since it's equal to y. So now that we have all that, we'll just draw a picture of R3. Okay, so we have, let's draw the plane first. I think that probably would be the easiest. Z equals y. So as y varies, z varies directly equal to y. So the plane, when projected onto the zy plane, it'll just look like this. And then if we wanted to add a bit of dimension to it, it would sort of be like that, going up like that. Does everyone sort of see that? And then we have the cylinder, and we know that the cylinder's radius is 2, because we have the sum of squares equals to the radius squared. And the center of the cylinder are going to be the values of x and y, such that each of these things here is 0. So we'll see x would be 1, x minus 1. Y would be 2, because we have y minus 2. So then we'll go 1 unit in the x, and then 2 units in the y. So the center will be like over here. And the radius of it is 2. This is 1, this is 2. And if the radius is 2, it will look like this. And you see that the cylinder will dice. But we will see that the plane will dice the cylinder and create an ellipse. Because you slice it at an angle like this, you chop it up like this. If you chop it perfectly horizontally, you'll get a circle. If you chop it at an angle, you'll end up getting an ellipse. Anyway. So that's a rough idea of how you draw it, but yeah. Other questions about that? It makes sense for the most part. Okay. Yes, cool.
So does it end up looking like one of those climby things on a playground? Like the little spirals?
Well, it'll be an ellipse. Are you saying the curve of intersection?
Mm-hmm.
Yeah, it'll be an ellipse.
It's an angle.
Yeah, because it's angled. You have a cylinder and you're dicing it at an angle, like this.
Okay.
That was an interesting one.
Yeah, you're right. Yeah, that's
There were some interesting true false things in the beginning. So the true false is, ooh, the direction to the sun, you're vector, the sign, alpha, beta, gamma. Angle alpha is measured from x, it's measured from the x-axis. So then it's just known the fundamental, like, things.
So we're asked to find the distance between the two following parallel planes. So plane 1 is 2x minus 3y plus z equals 4 and 4x. Alright, so first we see that it is parallel because the normal vector here, remember, the equation for a plane is that I do n vector dot r minus r0, which these are all right? So the normal vector is what corresponds to my coefficients in front of x, y, and z. So here my normal vector corresponds to what? What is the first one?
2, -3, 1.
2, -3. And is 4. Okay. Now, the idea for this, to find the distance between it, I'm going to find a point on my plane 1, right? So, say I have a second one that's parallel with it. I can find the normal vector, right, and find the corresponding distance between the two planes, and then subtract. So find a point that's on this one, and find the closest point corresponding on that plane, and subtract. Okay. Find the distance in between. So first, I take this 2, -3, 1.
You think that's easier than this one? More room to-
That might be easier, yeah.
Gotcha. I would probably.
Okay, so what we're going to do is we're going to find a point on one plane, find a point on another, actually in another drawing, we just draw it bigger. I'm going to find an arbitrary point on the first plane. Then I'm going to find an arbitrary point on the second plane. Then what I'm going to do is I'm going to take the displacement vector between those 2 points. I'm going to take the normal vector for both of the planes, because that normal vector will be the same. And that vector will be like this vector right here. And then what I'm going to do is I'm going to take the composition of this vector onto the normal vector, because that will give me this length, which is the distance between the 2 planes of the scalar. Does everyone see what I'm going to try to do here? Okay, so we'll find a point on plane 1. We'll call that let's call it P, P1. Lowercase, so it's not too confusing. So we need a point x, y, z that satisfies this equation here. So I think the easiest point might be 0, 0, 4. Does everyone see how that would satisfy that? So 0, 0, 4. And then we need a point on the other plane. And let's think about what the easiest point would be. Maybe 0, minus a half, and 0 might be a simple point. So you get 0, then minus 6 times minus a half, you get 3. And then plus 2 times 0, you still just have that 3. So we have 0, minus a half, and then 0. So now I'm going to take the displacement vector. So it'll be, let's say P1 minus P2. So we'll get 0 minus 0 is 0. 0 minus negative a half, we'll get 1/2, and then 4 minus 0, we get 4. Okay, so this is V right here. That's this displacement vector between P1 and P2. So now I'm going to take, I can pick whatever normal vector I want. I'll choose this one here. So then we have, this is N1, or just N, which is right here. So we have that. And then what we're going to do is we're going to take the composition of V onto N, and that will give us this scalar distance here, and that shadow of V onto N actually ends up being the shortest distance between the planes. Does everyone see how that would work? Yeah. So I'm going to go ahead and calculate this. So this will be N dot V over N. So we can just plug some stuff in here. So N is, well, it'd be 2 minus 3 and then 1. Dotted with V, which was 0, 1/2, and 4. And then over the magnitude of N, so it'll be the square root of sum of squares. So it'll be 2 squared plus minus 3 squared. It's 1 squared. So if we dot the 2 of those vectors, we'll get 2 times 0 is 0. Minus 3 times a half, we get minus 3 halves. And then 1 times 4, we get 4. And then we have the square root of 4 plus 9 plus 1. So 4 is the same thing as 8 halves. So 8 halves minus 3 halves, we get minus 5 halves over the square root of 14. So you get minus 5 over 2, the square root of 14. But then because distance is always positive, we take the absolute value of that, we get 5 over 2 squared root of 14. And that should be the answer. Go. Yeah, sure. Questions? Yes?
I probably missed it, but where did you get the P1 and P2 from?
We picked we picked an arbitrary point on plane 1, which is, we chose it to be 0, 0, 4, so that satisfies the equation.
Got it.
And then we picked an arbitrary point on plane 2, we chose, that satisfies the equation, and that was 0 minus a half, 0.
Okay, got it.
Yeah.
Thank you.
Out of curiosity, is the other way using like the square root of ax1 plus?
Oh yeah, that way. I think plane, that's the distance between a plane to a point.
Couldn't you use that?
Find, yeah, actually, you probably could, we probably could have used that.
I think it
What's
would
the
take a
other
bit
way
longer
you-
than this, because, or at least more.
This, yeah,
Algebra, this is the way that with the shortest amount of algebra
Right.
to do it.
Because I remember discussion.
Yeah, I remember, yeah, someone, one guy said, I can figure out how to do it. I figured it out, I figured it out.
Yeah.
Yeah, I remembered how to do it. Yeah, this is.
Because this is definitely way easier
Oh, it's
than
way
the way
easier,
you explained to us.
Which is why I wanted to make sure we got it right this time.
Yeah.
Yeah, so there's no confusion.
Yeah. That's fine. And actually, this makes so much more sense.
Yeah, you just find arbitrary point on P1, arbitrary point on P2.
Distance and then just
Take the displacement vector, so that's a vector that if you had it start at P1, it would
Yeah.
point and travel all the way to P2. Then you take normal vector of either plane, because it's the same normal vector.
Exactly.
And it doesn't matter what the magnitude is, because in the formula, you're then dividing by, oh, I forgot that put, actually, I forgot to put the magnitude by, you're dividing by the magnitude of it, so it doesn't matter what the magnitude is. And you take the composition of this vector onto the normal vector. And we learned that if you do that, you end up getting that length between
Yeah.
two planes. Yeah, in this case, it ends up being the distance, the shortest distance between two of them.
So
Yeah. Maybe if I drew it in R2, it might be a better visual. So we have plane 1 here, we have plane 2 here, and then I'm picking an arbitrary point on P1, an arbitrary point on P2. This is P2, P1. I take the displacement vector between them, and then I take the normal vector, and then you have that, yeah, and then you have that this length, well, because really the normal vector could be all the way up here, it could be arbitrary length, but then this length here, the shadow of this displacement vector onto n, is going to be the composition of a displacement vector v onto n. Does this visual make sense? Yes.
At the end, the minus sign just went away because we only care about the magnitude.
Yeah, we only care about the magnitude.
I
put
should
the
have
distance between. Yeah. So I guess the proper I should do this.
And also, yeah, you brought up a very good point. Actually, another way to solve this is you can use this whole equation that D is ax naught plus b y naught plus c z naught plus d over the square root of a squared plus b squared plus c squared. So all I need to do is to make sure that I choose a plane and point that are different. So one, x naught will be on the other of the points, right? Other of the planes, then a, b, c, d. And then I can simply go, for example, I chose 2, negative 3, 1. And then what's d in the first case? Negative 4, because you need to move it over, right? This is if ax plus by plus cz plus d equals 0. So in that case, I have 2, negative 3, 1, negative 4. And then I'm choosing the point that comes from the second one, which is 0, negative a half, 0. And that just kind of guess and check, right? Not guess and check, but you can find some way, find some point by sending all of them to 0 and just finding, right, send 2 of them to 0 and finding the other one to make the equation true. And that's a point on the plane. For example, we did 0, negative a half, 0. You could do other ones, it would still work. Just make sure that when you plug that back into the second equation, you get 3. Then, you just multiply, right? 2 times, in that case, 0, minus 3 times minus a half, 1 times 0, minus 4 over that, and you get negative 5 over 2 square root 14. And then remember, distance is a scalar quantity, right? So the distance between here and here is not a negative number, it's just a number, right? That just happens to be one of them, so you take the absolute value, and it's 5 over 2 square root 14. That's actually a much easier way to.
Because I was thinking, like, that makes sense too.
Yeah, I mean, yeah, that's probably how this came out, I guess.
Yeah.
Okay. Get that. We needed to
So now, let's do.
Oh.
first of all, I said this in my description. Let's say that you're given some R of t, and you want to find the acceleration of that particle at some point. Do you first plug in that number into R, and then take the derivative, or do you find the second derivative, and then plug? Find the derivative. And that's the same. I can't go to the first derivative and then plug it in. I need to go all the way to what I'm trying to find. In that case, acceleration, so second derivative and then plug it. All right. Besides the point, what I want to say now for R of t, right, we have R of t, right? Now, how do I get that to t of t? So R of t, I'm going to take its derivative. I'm going to get R prime of t. So t of t is R prime of t over the magnitude of that R prime. Then I also have the normal vector of t, which is t prime of t over the magnitude of t prime of t. Now, b is what?
T cross t. Or is it n cross t? I think it's the n cross t.
I think it's n cross t.
Yeah.
We can look at it.
No, it's t
No, I don't think so.
It's t cross n.
Okay, t cross n.
All right. All of these are really good. Now, right, so all of these, if you're ever asked to find the normal vector at some point, you should first find the general expression for n without without plugging in stuff, and then you can plug it. Right? So you need to do all the derivatives beforehand. Okay. And then other form. K is curvature. The curvature is t prime of t over r prime of t. This is magnitude. Okay. But it also equals something else. It also equals r prime of t cross r double prime of t over the magnitude of r prime of t cubed. Notice the magnitude signs here, right? Cross product returns a, but the curvature is a scalar, so I need to take the magnitude. Okay. All right. So now let r of t equal to t cosine of t and sine of t. Then I need to compute t prime and its magnitude. To find t prime, I need t. To get t, I need r prime and its magnitude. So let's find r prime. R prime of t equals 1. Derivative of cosine is negative sine of t. And derivative of sine is cosine. Okay? Now, the magnitude of r prime of t. It may seem a little bit weird that I can find the magnitude of something that doesn't have numbers plugged into it, right? But look, if I take the square root of 1 squared plus negative sine of t squared plus cosine of t squared, I'll end up getting the square root of 1 plus cosine squared plus sine squared, which is also known as 2. Right? So the end is root 2, because cosine squared plus sine squared is 1. So the magnitude of r prime is the square root of 2. So now I can go and I can say that my t of t is equal to 1 over the square root of 2 times my r prime vector, which is 1, negative sine of t, and cosine of t. Right? So everyone's with me on how I got that? Then I need to take its derivative, t prime of t, equals to 1 over the square root of 2 times 0. Derivative of negative sine becomes negative cosine of t, and derivative of cosine becomes negative sine of t. Right? Now I need its magnitude, magnitude t prime of t equals square root of 1 over the square root of 2 times negative cosine of t squared plus 1 over the square root of 2 times negative sine of t squared. Do not forget this 1 over 2. Don't just plug this stuff in, because t itself has this, which will definitely affect its magnitude. Okay? All right, so this equals square root of 1 over square root of 2, 1 over the square root of 2 squared, right, is 1 over 2 times negative cosine of t squared, which is cosine of t squared. Then this will also be 1 over 2 sine squared t, right? So this ends up being what? Because I have also one giant square root out of this, right?
Yeah.
And it ended up that this is just magnitude 1, right? Because it's cosine squared plus sine squared. So then the magnitude of that times the magnitude of that ended up with my final answer, 1 over the square root. Okay? So I can do it that way also. Now, n then is t prime over this. So what does that mean? So it's 1 over the square root of 2 times 1 over that. So it's dividing by, right? So 1 over that is just multiplying by the square root of 2. But then also times my t prime, which is this. 2. Zero negative cosine of t. Wait, what happened?
Yeah, why is there?
That's not
Right.
what happened. Zero negative cosine. Right, because if I take something, also, this, all of these things, t of t and n of t are unit vectors, right? So this will have a magnitude of 1, right? Not its derivative, but the thing itself will have a magnitude 1. Here I can check and make sure that I'm right, and the way I was like, hey, okay, something was wrong. Because this should have magnitude 1 at the end, because I took something and divided it by its magnitude. So if I take something and divide it by its magnitude will be 1. So here, cosine squared plus sine squared is 1, so I can go, okay, this is a unit vector. This is correct. I can also then go and try and calculate k for, let's say, t equals 1. So k for t equals 1 will be curvature in general, which is t prime, the magnitude of t prime of t, which is 1 over the square root of 2, over the magnitude of r prime, which is the square root of 2. So 1 over the square root of 2 times 1 over the square root of 2 is 1/2. Now, how do I evaluate that at t equals 1? So what would you, if you had, like, this is a free response, if you said, here's this, tell me the curvature at time t equals 1. What would you say? It would be 1/2, right? It doesn't depend on time. Okay, so it's okay, it doesn't have to. In this case, it didn't. The more complex that this gets, the more likely that it is going to be dependent. But if it's not dependent, it's not dependent. That means that time at t equals 1 equals just curvature in general for any time, and it's 1/2. So it's okay, that can happen. Anyone have any questions on that? Okay.
Here's a question.
Yeah.
Could you like name out what every letter is? So like the G.
Yeah. It has to do with the right handle. There's a good image for it. Show it.
Like, where is it on a curve?
Like, what is it called or what is it?
For t?
Yeah.
The tangent vector to the curve.
So let's say this is your point, right? My tangent vector is what you would think of as a tangent vector, right? Then imagine, so this is a curve, right? This is a curve. The normal vector of curve will always point towards the center of that curve. So as this goes, for example, let's say it curls downwards, right? here my normal vector will be downwards, here my normal vector would be upwards if I had it. This would be my tangent, this is tangent, this is normal. Yeah, this is.
For the previous problem, what was the answer for K again?
Okay, so we have this curve here, and yeah, we want to find the arc length of it from this point to this point. But the thing is, we need to know the values of t that correspond to each of these points on this curve. So, does anyone see something we can look at in RT? Yes?
The middle one is just t.
Yeah, right. So we see the middle variable, the variable for the j component of RT corresponding to y, t, is just t. And it helps us see that t goes from 0 to pi over 2, because we see 0 is the j component of this vector, of this point here, and pi over 2 is the j component of that point there. So you see t goes from 0 to pi over 2. So what we'll do is we'll just use the formula for arc length. So arc length, the formula for that, it'll be the integral from t equals time a to t equals time b of the length of r prime of t, dt. Does everyone remember this? Great. So yeah, we have this is the formula for arc length, and we see that a is going to be 0, and b is going to be pi over 2. So this is our t. We need to find r prime of t, and then take its magnitude. So we'll go ahead and figure out r prime. So r prime of t, derivative of cosine will just be minus sine. Derivative of t will just be 1, and derivative of sine will be cosine. So then we just take the magnitude of this. Just be the square root of the sum of square entities. And you see this will end up being square root of 2, because the sine and cosine squared will collapse to 1. So just get square root of 2. So we'll just plug in the square root of 2 here. And the integral of a constant over some interval will just be equal to the constant times the length of the interval. So the length of the interval we see is pi over 2. So this will just be pi over 2 times root 2. That's it. Any questions about that? Pretty straightforward. Okay.
We're nearing the end. So, first question that I have, actually, this is like the second one, the previous one. So I didn't really say it too much.
if this is tangent vector and this is your normal vector, right? Does your B vector point out of the page or into the page?
Out.
Right, out. Because what I do, so the right hand rule, if I'm doing T cross N, right? This is B, okay? So what that means is that I'm going to take my right hand. By the way, from personal experience, it's important to use your right hand. If you use your left hand, you'll get the wrong answer. So, not to say that I've ever done that before. So you point your fingers, right, 4 fingers, in the direction of T. Okay? The first one. And then you're going to, then you're going to cross it, start curling your fingers towards N. Right? Then if your thumb is pointed outwards, then the resultant B vector will be outwards. If it's into the page, for example, if my T was this way, right, then my T would be here, and then I would cross up towards N, and it would be into the page. Okay? So it depends on where my T and where my N is. Right? So if this was an outward one, so this is out of the page for me. If it was like this, my T is here, my N is here, T, N, this would be into the page. This is in, this is out. Does everyone understand that? So now,
I also have another way, sort of interesting way. So we know that if we cross I and J, we end up getting K, right? So what you can try to do is imagine rotating this vector triad onto T and N, where T would be I and N would act as J, because we have T is on the left side of the cross product and N's on the right. And if you rotated that onto here, you'd see that you'd have this would be I, this would be J. So then K, after that rotation, it would still be pointing up like this. And that way you know it goes out. This is just another way you can figure out which direction the cross product would go. Did everyone see that? So we sort of just imagine rotating this onto T cross N.
so I think one of the last problems that we'll do is, remember this whole thing with how I can try and understand what's happening with a big scary graph by splitting it into many 2D looking graphs like we had on that quiz, remember the one that was not. So here he's being,
I'm still being
x squared is z squared.
Z squared minus x squared minus y squared equals 1.
Alright, so I need to do this for x, y, and z equaling to k, for k equaling 0 plus minus 1 plus minus 2. Okay. Oh, nice. So, let's first look along z-axis. So here we're going to let z to equal k, and k, let's do for k equals to negative 2. For k equaling negative 2, what am I going to get? So here I'm going to get negative 2 squared, that becomes 4 minus x squared minus y squared equals 1. This is also known as 3 equaling x squared plus y squared. And that is a circle with radius square root of 3. Right, and this is going to equal negative 2 and 2. Because it's squared. Now, let's go ahead and take a look with k equaling negative 1 and 1. What do I get there? Here I'm going to get that 1 equals minus x squared plus y squared equals 1. So that means that I get what? So if I get 1, 1, what does that actually mean?
X squared plus y
it's just a point.
Just a point. Okay. So what this is saying is that as I look at it on the xz plane, I'm sorry, xy plane, right? I see, so I'm just looking topically down, x and y, right? At z equals 0, I'm sorry, at z equals -1 and 1, I get points, okay? And as I go to 2 and -2, it becomes some circle radius square root of 3, right? So now we can see even more what's going on by going at k equals 0. So here I get that -x squared minus y squared equals 1. So this means that x squared plus y squared equals to -1. So what does that mean? How do I graph that? There's nothing. It's imaginary. So on the real plane, I can't show it. This is imaginary. Okay, I can't graph in the real domain. Okay. So that means that for
For the middle one, why can't you make it x equals y and x equals negative y? Why can't you make it x equals y and x equals negative y?
x equals y and x equals
The-
negative.
the- the- For the middle one.
You graph that down. Like you need values.
Yeah, the cross.
What? But like what values are you plugging in? Because you have to plug in values to graph it.
So like, if x is 1.
Just give me numbers to plug in is what I'm asking you.
I don't understand what you're saying.
Like what number could you plug into that equation?
What are you using?
Okay, so here the question is to plug in x, y, and z equals k.
So
Here,
for
and-
1 and -1.
Right.
So if x squared minus y squared equals 0,
Right.
then x squared equals y, the negative x squared equals y squared.
X squared equals -y squared. Okay.
So then can't
You
you
may
make,
be thinking, okay, you're just gonna take the square root.
yeah?
Okay, so if I take the square root, I'm gonna get that x equals the square root of -1 times y.
I see the problem.
You're good. Okay, now I understand what you're saying. Yeah, so this is by definition just a point. It's a circle with radius 0, right? So there's no way you can manipulate it to get some graphs out of it. So that's, I understand what you're saying. Okay. But yeah, you don't want to do that. So when you take the square root, remember you're taking the square root of the whole thing. So it wouldn't be possible. Okay, so now let's do it. Z we did, X we can do. Right? Z squared minus K squared minus Y squared equals 1. Now we're going to do it for K equaling minus 2 and 2. Alright, so here I have that Z squared minus 4 minus Y squared equals 1. So here I'm going to get that Z squared minus Y squared equals 5. Alright, so now how do we graph that? That's a great. So it's one of those that goes both ways.
Yeah.
We need to figure out which one is positive. So one way that I can test this, so if this is a y-z plane, so let's say I don't remember, right? You don't remember. Okay, at y equals 0, right? At y equals 0, z has to equal plus and minus the square root of 5. Minus the square root of 5, and this is positive square root of 5. Okay? Now, at z equals 0, this is imaginary. It doesn't exist, right? So for z equals 0, there's nothing going on right there. There's no values of y that this works. So there's going to be some limiting that happens, right? And actually, for z equals the square root of 5, that's when y is 0. Okay. Now we can choose any other point. Let's say y equals 1. So z squared would equal 6. Well, let's see what other value. Let's say z equals 2. I mean y equals 2. So 4.
Well, you have the vertices.
Yeah. Let's say it's somewhere there. So for y equals 2, we have that z squared equals 9, right? And z is, and this is also for minus 2, right? Because it's squared. Z is plus or minus 3.
y equals 2 and negative 2, z equals plus or minus 3, which is over the square root of 5, because 3 is the square root of 5. So it's something here, this is 3. So I can start to trace. And that intersection is the square root. Okay. So we did that. Now we can do the same for
Do we have
So now I get z squared minus y squared equals 2. So here instead of it equaling 5, it equals 2. So it's going to be the same, except that this now reaches the square root of 2 and negative square root of 2. And it's going to curl out like this. Now at 0, k equals 0, I get that z squared minus y squared equals 1, or that z squared equals y squared plus 1. So now my point of intersection is 1 and negative 1. Alright, so now, here, we saw that at negative 1 and 1, a point started to arise, right? And here, I also agree, and anything that was less than that at 0 was imaginary, right? And here we're also seeing that the graph is only valid for points that are greater or less than 1 or negative 1, right? Now, I'm not going to write it out again, but I can see that x and y have the same relation, right? So actually, this will be both for x and for y, right? So this will both be true for x and y. So what I can actually now see, and by using my knowledge of how this is being a circle, I can see that in a 3D graph, right, this point, a circle is going to be created for all of them. So this is at 1, this is at negative 1. Sort of curl in. Does everyone see what that looks like? Yeah.
If we see that, so we're doing this question, and we see that they're gonna have like the same relationship for the, or like they're gonna behave the same way for both x and y.
I would look at the wording of the question. If the question asks you to do it, I would.
Okay.
I mean, just to be totally honest, it's not us grading like that. If the question asked you to do it, I probably would.
Okay.
Yeah.
Do we have to separate all the graphs for?
No, you can combine it. You can combine it. Like what I did, negative 2, 2, negative 1,
Right.
or even if you want to do it on 1 for all of them.
Yeah. Okay.
As long as you did graph it and illustrated that you graphed it. But you guys can see, right? Even though you may not know how to graph a parabola, may not know how to do that, you can also test points, right? Like I didn't immediately know how to graph that, but I tested some points and I was able to construct together what it is. Right? You don't even have to know it. You don't have to know how to test your way of graphing stuff. It should be easy for you to at least test points for it. Okay, everyone good? One last question. Okay, then we can do that. 2 more questions.
so we have a curve that is just purely in R2, just a curve of a y equals function of x. So we're in the xy plane. And we want to find the curvature of this function at time x equals 1. So we'll have to use the formula for curvature when we have y as a function of x. So it'll be f double prime of x over 1 plus f prime of x squared to the 3 halves. That's just what it ends up being. Where,
Do we need to have these memorized?
yes, you will need to memorize that, unless you want to derive it, but that would be much harder. Yeah, I don't know. Also, they would take more time to do that, so yeah, you want to remember this. So, yeah, we'll have to find f prime of x and f double prime. So f prime of x will be 3x squared plus 1. So f double prime will be 6x. So then we just plug this in here. So this will be 6x over 1 plus 3x squared plus 1 squared, 3 halves. And then we want to evaluate this x equals 1. So we'll get 6 over 1 plus 3 plus 1 squared to the 3 halves. So we'll get 6 over 1 plus 16 3 halves. So we get 6 over 17 to the 3 halves. Any questions about that? No? Makes sense. You just need to know the formula and then you just plug everything in. All right. So,
we also could do
So, all right. Now, when we talk about acceleration, so, okay, velocity we think as what? As a scalar, but kind of also what it's just. Velocity is technically a vector, as in, I'm not moving 5 miles per hour, I'm moving 5 miles per hour this way, right? My speed is 5 miles per hour. For acceleration, there is a vector that we have, but the vector is kind of split into 2 parts. So acceleration has both an acceleration in the tangent direction component, but also an acceleration in a normal direction. Right? Because it's not to say that, first of all, my velocity will always be in only one direction, right? It's not going to be, it won't have a tangential and normal component. My velocity will just be the way I'm moving, right? If I'm moving this way, now you could split that up as I and j, but all of my velocity will be tangential because I'm moving that way, right? So, but who's to say that I will continue moving this way in the future? If I'm on 195 and it curls like this,
My speed, if I'm here, my tangent direction is here, and my speed is this way at that second. But later on, I will end up moving this way, right? My velocity will have changed. Now, when we talk about derivatives, that's change in something per some time, right? So here, over this few seconds that I'm going from here to here, has my velocity changed? Let's say that this is 5 miles per hour, and this is, well, maybe 50, and then 50 miles per hour here, right? Well, I mean, if it's 195, maybe. If 195, that's like 80. Maybe like 695, that's like 5. But, right, here I'm 50 miles per hour. Here I'm still 50 miles per hour. Has my velocity changed?
Yeah.
Yes. Has my speed changed? No. But my velocity has. And so therefore, my acceleration will be a non-zero number, right? So here I'm 50, here I'm 50, but my acceleration is non-zero. And that's because, well, my tangential in this case is 0, right? My speed is the same. My actual normal component, which just means that my velocity will start moving to the left over time, right? Because that's where the center of the circle is. That component will be non-zero, right? But let's say that this ended up being 60 miles per hour, then both will have a value. Right? Okay, so now let's get into a little bit more equations. A of t, tangent component is what we think is the change in my velocity, is the speed, and that is equal to r prime of t dot r double prime of t over the magnitude of r prime of t. Now, the normal component is also known as curvature times the velocity squared, but that's also equal to, oh yeah, right, so it's the tangent component in the tangent direction and the normal component in the normal direction. So this is a scalar, right? AT is a scalar, but it's the scalar in the tangent direction. And A sub n is a scalar, it's a number, but it's in the normal direction. Right? So that's what makes my total acceleration vector. Now, this is equal to r prime of t cross r double prime of t over the magnitude of r prime of t. And I'm missing something from this equation, and I want you to clarify this.
Q magnitude.
Magnitude. Right? So A sub n, as I said, is a number. So this is the magnitude of that. Okay? And there's somewhere else. Remember that whole, we should write these equations down. A dot B equals magnitude of A, magnitude of B. Dot product is cosine. And then A cross B equals magnitude of A, magnitude of B, sine theta. But what is this missing?
Magnitude of the cross.
Magnitude here, right? So don't get so concerned. You're like, oh my gosh, this is a number and this is a vector. I'm just going to throw it in an equation box and give it to him and hope that he gives me points. Just remember that you need to take a magnitude of it. Don't forget that. Now, here I'm taking the magnitude of it. So, let's give an example. Let's let r of t equal to 1 t squared. Okay. Let's find A as a total vector for t equals 1. All right. So, I also want to clarify something. This is something you may see in the exam. Here's one way of writing this. For t equals 1. Or I could also say, for the point 1, 1, 1. Does everyone know how to combine, how to move from one way to the other and the other to the other? Right? Here, this is t equals 1, so that means that the particle at its position is 1 times 1 squared, which is 1. Also, if I'm given this, I should be able to know that t is equal to 1. He doesn't need to explicitly tell you t is 1. He could tell you this, and you should be able to work your way back here and find that t is equal to 1. Okay, and you know, for example, here, this is t squared. How do I know it's not minus 1? Because here, this one has to be, right? So this has the possibility of being -1 or 1, but this only can be 1, so my t is 1. Okay. Now, r prime of t is equal to 1, 1, 2, t. R double prime of t, 0, oh yeah, that is 2. 0, 0, 2. Right? Now, let's do some things. R prime dot with r double prime is equal to what? 0, 0, 4t. Right? Now, it crossed, r prime cross r double prime is equal to I, j, k, 0, 1, 2t, 0, 0, 2. Put my hand over I, multiply 2 minus 0 in the I, minus something in j, it's 0 minus 0, 0 in the j, plus something in the k, 0 minus 0 is 0, so it's only 2 in the I. That's my cross product. What's the magnitude of 2 in the I? 2. Good. So the magnitude of that becomes 2. I also want to ask, just, this is, this is not related to the problem. Sometimes, this was one in your quizzes and some of you messed up. If your vector comes out to be this, 1, 1, 1, right? What's the magnitude of that? It's not 1. It's the square root of 3, right? This is equal to square root of 3, and it's not 1. Just watch out for that. Here, because it's only one term, you can just go out and say that. But this is not equal to 1. Okay, so it's equal to 2. So now, let's also find the magnitude of r prime of t. The magnitude of r prime of t is what? Square root of 1 plus 4t squared. We'll just leave it as that.
Shouldn't you put the magnitude symbols around?
Yeah, you took a bar on the right.
Alright, so a sub t then here is equal to what? R prime of t dot r double prime of t, which is 4t, over the magnitude of r prime of t, which is the square root of 1 plus 4t squared. Right? Now, a sub t, this is just a sub t. But if I want to find that at t equals 1, then that's equal to 4 over the square root of 5. Everyone see that I plugged in? After I took all the derivatives and cross products and divisions. Now, a sub n is the cross product, the magnitude of the cross product, which is 2 over the square root of 1 plus 4t squared. That's a sub n. A sub n, evaluated, t equals 1. 2 over square root of 5. Okay. Now, we're not going to go through and find the tangent of the normal vector. You could, right? We know how to take the derivatives here and plug in the points. You could find the tangent and tangent vector and the normal vector, but we don't need to right now. It's okay. Let's just find a sub t and a sub n. We did that. We know that that's in the tangent direction, this one, and this is in the normal direction. Anyone have any questions? Okay. Only one other thing that I'll say. From the very first quiz, remember how we had this one question that was like summing up vectors? Remember the crow and the wind? Does everyone remember how to, do you want to go through that again, or do you think you got it? Right, just remember, you add vectors here, and then you start the next one at the end of where that other one was, right? And then you combine it together. You can do it by subtracting this with its initial point.
You can do a further question.
Okay. Do you want to do it? It seems like people want to go. But we can do it very quickly. Okay, very quickly.
Doesn't look like you should take that.
There's a lot of. Okay. So the rowboat is moving due north at 28 knots. So due north is upwards, right? Here is 28 knots. The current in the lake is moving to the southwest. Southwest means down to the left at exactly 45 degrees.
Perfectly southwest.
Right? So here, right, this is the way it's going, but I'm not going to start it from the origin again because the bird has now moved up here, right? I'm not going to have the bird teleport up here and then also affect this way. It's going to start directly where this was, right? And this is magnitude what? 12 square root 2. Now, many of you I'm sure are in or have taken or will take physics, and in here we need to know how to split up our vectors. This is one vector that's directly 45 degrees, and I know then that I can split this vector up into two, right? We know that this is a triangle, 1 square root 2, and so if this magnitude is 12 square root 2, then this becomes 12 and this becomes 12, right? I can split this 12 square root 2, so this won't even reach anywhere near the origin. Let's just say there, right? This splits into being 12 units downwards, and then 12 units left, right? So now I'm summing up what I have. I have an upwards 28I from the wind. Sorry, yeah, J. 28J from the wind, that's upwards, right? So it's J. This is J. Minus the 12J from the downwards component. I think this is actually just flying, right? And this is the downwards component.
Yeah, the rope goes rowing.
And then minus 12I from the leftwards component of the wind. Right. So when I sum all these together, I'm going to get that it's minus 12 in the I plus 14, 16 in the J. Or also known as 12, 16. Right?
Negative 12.
All this stuff. Sometimes a different place. Oh, and then I'll find the speed. Okay, find the speed. Try to find the speed, right? Square this, square root.
Oh, and then units, not.
Good luck.